Okay, so now a look at another three-dimensional coordinate system. This one is called the normal, tangential, binormal coordinate system. And the binormal direction is not that important or useful to us, but n hat and t hat are. This coordinate system is useful for a particle moving along a curved path, so curvilinear motion. And the tangential direction is just defined as the direction the particle is actually moving. It's tangent to the curve. Perpendicular to that is the normal direction, the inwards direction, and that will be directed at the local center of curvature. And there's a radius of curvature here, which is just comes from the circularization of this path locally at that location. Now, if this were a circle, then the radius of curvature is just the radius of the circle. But say for a parabola, which is not a circle, you can still find a radius of curvature, and it varies along the track. So the velocity just has a tangential component. There's no normal component to our velocity vector. And to find the acceleration, we're going to differentiate that, of course. We run into an interesting problem, though, of course, here, because the t hat vector is not constant. So these are both functions of time, and we'll have to use the product rule. You see, if the particle had reached this point on its trajectory, now the t hat direction is going this way. So we see that it's not a constant function of time. Unlike, say, I and j and k, which don't change, the t hat direction does, and consequently, we'll have to take derivative here using the product rule. Okay, so there's going to be two terms here, the rate of change of v in the t hat direction, and then v times the rate of change of that t hat vector. Now, this is, of course, the rate of change of speed. This is what we think of in Physics 11 as the acceleration. But there's actually two acceleration components here. So there's the rate of change of speed tangentially, and then there's something going on with the rate of change of the tangent direction. Now, we end up being able to prove that the rate of change of the t hat vector is v over rho in the normal direction. We'll prove that later. So we end up then with two terms. First of all, a changing speed term in the tangential direction, and then in the normal direction we end up with a term of v squared over rho. Now that's very familiar from Physics 12. We know that there's a changing direction when you're moving in a circle. Even moving in a circle at constant speed, there's an acceleration and a changing direction term v squared over r. So this actually is a familiar term. Now the radius of curvature, if you're moving in a circle, is just r, but if you're not, this is how you find it. And this is a Calculus 1 result that we'll discuss a little later in class. So if you know the equation of the path that you're following, y is a function of x, differentiate it, square it, add 1, root it, cube it, and then divide by the magnitude of the second derivative at that point. A quick example. Let's say a particle is moving along this curve. This is an inverted parabola, and at the point 2, which is right here, we're given the velocity, so we know how fast it's going. It's 3 meters per second. And the speed is increasing at this rate. Well, the rate of increase of speed is dv dt, and it's increasing, so it's positive. It's 0.3. That's given information there. So positive 0.3. Okay, so we're asked to find the resultant acceleration of the particle at that point. Well, we've just shown that there's actually two terms there to consider. There's the rate of change of speed, we have that one, and then there's the normal component, v squared over rho. So we're going to need the radius of curvature. So here's our function, and the radius of curvature formula requires y prime and y double prime, both of which are simple to find. Now we're going to substitute in x equals 2, and so we'll get a y prime of negative 4. A slope is negative of the tangent at that point. And so now we're ready to calculate that radius of curvature. Here's the result, which is really just a Cal 1 problem. So y prime we know is negative 4, so square it, it's 16. Add 1, it's 17. And then we divide by the magnitude of the second derivative, which is 2. And this works out to, when you calculate it, 35.04 meters. That's the radius of curvature at this point. So if you imagine sort of this as being part of, say, the arc of a circle, that's what its radius would be. So our acceleration vector then, dv dt we said is plus 0.3 tangentially. V squared, the velocity is given as 3 divided by the radius of curvature normally. And that ends up being equal to 0.25 in the normal component. And then the tangent and normal accelerations are perpendicular to each other. So as you fall down this curve, the tangent acceleration will be this way. You're increasing in speed, and your normal acceleration is like this, inwards towards the local center of curvature. So your resultant acceleration, which is the vector sum of those two, is just the hypotenuse of those two perpendicular components. And so just using Pythagoras, you can find its magnitude, and it's 0.395 meters per second squared. So there's a simple problem in NTB kinematics. We'll try one more here. So this one kind of gets into a bit of dynamics, and we're going to imagine that there's a mass on this slope that starts off at rest and that then slides down and reaches a point down here, and then we want to find the speed, the slope angle, the radius of curvature, and the normal force at that point. Okay, so since it's sliding down a frictionless slope and it's going from x is 10, so let's draw our x-axis down here somewhere. There we go. And we're starting at x is 10, so that's here, and then we're ending at x is 5. You could use the shape of that slope to find the corresponding y values. So 10 squared 100, so that'll be y equals 10. 25.1, this will be y is 2.5. This is a frictionless track, so we can actually just use energy conservation to figure out how quickly it'll be going when it reaches down here, given that it started at rest up here. So mg times the initial height is mg times the final height plus half mv squared. And solving for v, we get 12.1 meters per second of speed at that point. Now for the slope angle, we'll use an idea from Calculus 1, which says that the slope of this tangent line is given by the derivative. Now the slope of a line, which is a rise over a run, is the same as the tangent of the angle. So tan theta is y prime. Differentiating 0.1x squared, we get 0.2x. So at x equals 5, theta is just the inverse tangent. Putting 5 in here, multiplying by 0.2, you get 1. That'll be a 45-degree angle. So now we'll find the radius of curvature. We've got y prime. Y double prime works out to 0.2. So once again, the radius of curvature formula, break it out here. So it's 1 plus 1 squared, it's 2. Take the square root, it's root 2, cube it, and then divide by 0.2. I guess I'll substitute that in. And that works out to 14.1 units, 14.1 meters of radius of curvature at that point. So again, you sort of imagine a circle at this point, and then the radius of the circle at that point is about 14 meters. Now, we're actually not in dynamics yet, but this question is asking us to do a little dynamics. It's asking us to find the force from the track at that point. So it's a frictionless track, so the only two forces acting on the object will be the gravitational pull of the Earth and then the inwards normal force from the track. Now that inwards normal force will be in the normal direction. So if we apply Newton's second law, the sum of the normal forces has to equal the mass times the normal acceleration. And we saw earlier that the normal acceleration is v squared over rho. So what forces act in the normal direction? Well, there's the normal force in the positive normal direction, and then outwards in the negative normal direction, there's a gravity component. Well, this gravity component is just going to be the familiar mg cosine theta that we remember from our previous Physics 12 course. The other component of gravity is just pulling us down the incline, and that's what's causing the speed to change. But this component right here, the mg cosine theta component, that's in the outwards negative normal direction. So if we look at this equation now, we see that we figured out the angle, it's 45 degrees. We are given the mass of the skier, or of the sliding mass. We know the speed v is 12.1, and we know the radius of curvature. So we can solve for the amount of normal force from the track, and it works out to 867 newtons. And so there's a few simple problems in NTB kinematics. And next we'll move on and we'll look at kinematics in cylindrical coordinates. Okay, so we've looked at kinematics in Cartesian coordinates and NTB coordinates. Here's another coordinate system. It is the r hat, theta hat, k hat coordinate system. So this is the same k of Cartesian coordinates. It's the z-axis, and it's pointing outwards up towards us. I guess this is really still the x and still the y-axis, but in this coordinate system, from the origin, we're going to measure the distance r, and from the positive x-axis, we're going to measure the angle theta. And if there was anything coming in and out of the page, that would be along the z-axis. So this coordinate system is fixed. Unlike the NTB coordinates, here's the tangential direction and here's the normal direction, which move as the particle travels along the curved path. The origin here is always fixed. Now, for our unit vectors in this coordinate system, we're going to have, if this is the radial direction, then r hat points like this in the direction of increasing r. The direction of increasing theta will be anti-clockwise in this case, so theta hat is perpendicular to r hat in the direction of increasing theta. Now, there's another angle of interest here sometimes that we need to do component analysis. It's the the radial tangential angle, and it's sometimes called or labeled as a psi. So it's from the radial to the tangential direction, and we'll often need that to do component analysis when we're doing dynamics. Okay, but let's focus on kinematics now. So first, let's start off by stating the position in cylindrical coordinates. Well, you're a distance r away from the origin in the r hat direction, and there's no theta hat component. That looks a little odd, but remember r hat varies, it's non-constant, and you can see that if you, to get to this point, you're just going in the r hat direction and you're going a distance r. Let's see what velocity looks like in cylindrical coordinates. There's the distance and there's the direction one more time. So for velocity, we're just going to differentiate that. Now we have to do the product rule. So we'll differentiate r first, and that'll be in the r hat direction, and then we'll leave r constant, and we have to do the time derivative of the r hat direction. So what's the rate of change of that? So let's look at a picture. So here the particle was at a certain point along the curved path. This is a little bit later. It's now over here. And you can see that the r hat unit vector is changed a little bit. There's been a tiny little bit of change in its direction. And it's going to be that the change in direction is going to be related to the little bit of angular displacement that's occurred in this tiny time interval dt. Now, what we want to find is we want to find the rate of change of that r hat vector. Now, we'll appeal to calculus here, and the rate of change of r hat is the limit of delta r over delta t as delta t goes to 0. Now, what's delta r hat? Well, that means a subtraction, so we're going to do r hat final minus r hat initial, and then we'll divide by time, and then we'll take the limit as that goes to 0. Here, let's just try moving that over a little bit because I forgot to write the limit. And I should set a good example and do that. So it's the limit as delta t goes to 0 of this. So I have to do this vector subtraction. Well, if you take r hat final and then subtract r hat initial by adding the opposite of this one, So if we turn that one around, then you end up with a resultant that's going to point in this direction. So this is delta r hat. That's the vector subtraction of those two. So you'll do r hat final, and then you'll add this one head to tail, and then your resultant will be like that. But I'm just going to translate my resultant over here. Now notice that that is in the theta hat direction. So r hat final minus r hat, this vector, which is delta r hat. First of all, it's in the theta hat direction. So we're subtracting two vectors, so we're going to get a third vector, and now we know what its direction is. We can state that it is in the theta hat direction. And then how long is it? Well, this triangle is very small. This angle is very small, and so we can sort of imagine this as being like the little arc of a circle. And because arc length S is r theta, this is going to be the length of that vector delta r hat. The radius is just this length here. That's going to be the length of our r hat vector times the angle, which is the tiny little delta theta between those two. Now, the length of r hat is just 1 because it's a unit vector. So we've got the length of delta r hat is d theta, and we know it's in the theta hat direction. So this vector then is going to have a magnitude delta theta. Sorry, that should be a delta theta. There we go. A delta theta, 1 times delta theta. So the magnitude of the vector is delta theta, and it's in the theta hat direction. Now, in the limit of very, very small delta t's, this just approaches the derivative. So it's d theta dt in the theta hat direction. Now, that's actually what I set out to prove, that the d dt of r hat has magnitude d theta dt, and it's in the theta hat direction. You could also, in a similar way, prove this using the same sort of definition of derivative, do the vector subtraction, use the arc length formula, and appeal to take the limit and change d theta dt and delta theta over delta t into d theta dt. So let's use that now and go back to our velocity calculation. Recall that we had written it, we had gotten it this far, dr dt r hat, and then we had r times dr hat dt. Now we can say that dr hat dt is this. It's d theta dt in the theta hat direction. Now, to clean that up a little bit, we'll introduce dot notation. So a dot on top of r indicates time derivative. So here's the time derivative of r. So we've got r dot in the radial direction. And then here you've got the time derivative of theta. That'll be theta dot in the theta hat direction. So if you know what your radius and angle are as functions of time, then you could state your velocity vector. Now, if we visualize that then, that second term, this r theta dot in the theta hat direction, because d theta dt is omega, then this is just taking us back to some elementary physics we knew before. The linear velocity of the edge of the circle is given by r omega, where omega is the time rate of change of the angle theta. So that part we've seen before. But this term here is a new one. And this is going to happen when we have a changing radius. So say we're not moving in a circle, say perhaps we're moving along an elliptical path like a planet would as it travels around the sun. Now you're going to have a radial component of velocity, which is r hat in the, r dot in the radial direction. And you're going to have this theta component, which is r theta dot in that theta hat direction. And so your resultant velocity is going to be the tip to tail sum of those two. Remember that that is purely in the tangent direction, right? The resultant velocity defines the tangent direction. and there's no normal component. So this was in NTB coordinates. This is now in these new cylindrical coordinates. Now, we can repeat that same process that we just did of doing a derivative to find out what the acceleration looks like in cylindrical coordinates. So we're going to differentiate velocity. Well, velocity was r dot r hat plus r theta dot theta hat, and now we need to do the time derivative of that. So here it is in ddt notation, here it is in dot notation. So we're again going to have to do the product rule here. So first we'll differentiate r dot and get r double dot. Then we'll leave r dot constant and we'll have to do the time derivative of r hat. Now here we'll have to do the triple product rule, which means just time differentiate them one at a time and leave the other two constant. So we'll time differentiate r first and leave the other two constant. We'll leave r constant and time differentiate theta. And then we'll leave r and theta dot constant and time differentiate theta hat. Well, the ddt of r hat we saw earlier was theta dot theta hat, and we'll now use the fact that the rate of change of the theta hat direction is, so this term here is going to be, need a bit more room, r theta dot, and then this is going to be times minus theta dot in the r hat direction. So now we'll gather all the radial terms, and you see we've got r double dot minus r theta dot squared. So that is the radial acceleration. And then we've got, in the angular direction, we've got r theta double dot, and then we've got two r dot theta dot terms. So that's the acceleration in cylindrical coordinates. Now, we've seen many of those terms before in our previous physics course because theta double dot is the angular acceleration alpha. So we've seen that what's happened there? We've seen that r theta double dot term before, and the r theta dot squared in the negative radial direction, well, that's just v squared over r. So this was it was r theta dot squared in the negative radial or inwards direction. So we've seen those two terms before. But there's a couple of other ones now. We have one related to an acceleration along the radial direction. And then we've got this other angular term, which is 2r dot theta dot. That turns out to be related to something known as the Coriolis force and the Coriolis effect. So, to summarize then, in cylindrical coordinates, this is how you find the velocity and this is how you find the acceleration. A reminder with what we've done in previous physics courses, what theta dot is and what theta double dot is. So let's just do a simple example here. Let's have an object that's moving anti-clockwise. So I'm going to have it actually move this way. Okay, yeah, the reason I want it anti-clockwise here is just that that's going to be moving then in the positive angular direction, in the direction of increasing theta. So if it's going at 6 meters per second, that's linear velocity of 6. What's happened there? On you. Oh, there we go. So theta dot will be v over r. That'll be 6 meters per second divided by 10 meters. So that is 0.6 rads per second. Now, clearly, the derivative of that will be 0. And the radius is just a constant, so there's no time derivatives there. So we can very quickly state the velocity. There's going to be no radial component, and then the tangent component will just be 10 times 0.6, which is just 6 in the theta hat direction, which is, of course, what we said it was at the beginning. That's what we were given. Now, for the acceleration, we're going to have, this is going to be 0, then this is going to be 10 times 0.6 squared. So 0.6 squared is 0.36 times 10 is 3.6 radially. And then theta double dot 0, and this is just all 0. So it looks like that. So overall, it is minus 3.6 inwards, and then it's nothing in the angular direction. But of course, this is just v squared over r. So if you took the velocity of 6, you squared it, you get 36, you divide by 10, you get 3.6 meters per second squared towards the center of the circle. So that really is the centripetal term. Okay, so that's the simplest example you could possibly do. So now let's add in acceleration. So this object is going to start off at rest, and it's going to speed up to 6 rads per second in 4 seconds. So you're going to get now an angular acceleration, alpha, of 1.5 rads per second squared. Now that means for theta dot, so now we can say that our final angular velocity, which is theta dot of course, is our initial plus alpha times t. And then we could integrate again to find theta, but it's not really necessary. Okay, so the radius is again constant, so the derivatives will just be 0. Okay, so now let's state the velocity here. So again, there's going to be nothing radially, and then it's going to be r theta dot, which is 5 times 1.5 t. That's going to be 7.5 t in the angular direction. So it goes faster and faster and faster with respect to time. That makes sense. Next, let's state the acceleration. This is also going to be time dependent. And then this is the v squared over r term. This term is 0, but here we've got a 5 times 1.5. So simplifying that a little bit, we get 11.25 t squared inwards, and then we get 7.5 in the theta hat direction. Now that 7.5 is r times alpha, right? So that angular A is r alpha, and alpha being 1.5 and the radius being 5, that makes perfect sense. So that's consistent with what we would have done before in elementary physics. All right, so a couple of problems here in cylindrical coordinates. And here we're given the radius and angle as functions of time. So first let's graph them. At time 0, this is just 2. So we are, and then the angle is 0. So if this is the x and the y axis, then this defines theta 0. So we start off 2 units out here on the x-axis. At point 1, this becomes 2.4, so the radius increases. We're up to half a radian now, which is about 30 degrees. So along that 30-degree angle, you go 1, 2.5 units. Then at point 2, that's 2.8 by the time we reach a radian, which is about 60 degrees. So we're now almost 3 units away from the origin. And then when we reach 1.5 radians, which is about pi over 2, we're now a little bit more than 3 units away from the origin. So this is a sketch of the parametric curve. So we see that the radius is increasing, so we expect a radial velocity in this case. The actual calculation of that's quite simple. If you do a time derivative of this, you get 4. If you do a time derivative of that, you get 0. Here we have constant angular speed because d theta dt is 0 and theta double dot 0. So we have a radial velocity component. It's a constant radial velocity. And then in the theta direction, it's r theta dot for the velocity. So that is time dependent. It's 4t plus 2 times 5 theta dot. So those are the two components of velocity, the radial velocity and then the angular or theta velocity. For the acceleration components, it's r theta double dot minus r theta dot squared, and then it's plus r theta double dot plus 2 r dot theta dot. Now theta double dot is 0, so that term just disappears. This time though we do have an angular term because of the r dot. It's 4, theta dot is 5. So there's our angular acceleration. Now, in the radial direction, r double dot 0, but we certainly have a term here, r theta dot squared. Theta dot's 5, so theta dot squared is 25 in the radial direction. So this is also time dependent. It's in the negative r hat direction, which will be inwards, and then this is 40 in the angular direction. Now, if we were to include the z-coordinate, it's very easy because the z-coordinate is just a Cartesian coordinate. Here we've got all three functions increasing, so at time 0 it's 2, 2.03, 2.06. Okay, then for the z function, it also increases with time. Starts off at 0, that's in the xy plane, and then it's 0.1 and 0.2. Oops. Now for the theta function, we start off at an angle 0, so we start off here on the x-axis, 2 units away, and we're down, because the z-coordinate 0, we're down on the xy plane. Then at time 1, it's 0.43, so that's, that's about 24 degrees or so, so it's about heading out like that. Now the radius is still basically 2 units, and then we're up 0.1 above the xy plane. So we're kind of spiraling up here now. Then if we put in 2 seconds, that's 0.8. And that'll be 0.92, so that's almost a full radian, which is basically 60 degrees. Now we're still basically at 2 units from the origin, so r is not increasing very quickly. We're now twice as high in the z direction. So this is a spiral, right? It's rising, it's getting further from the origin as the angle sweeps it around and around and around. So that's the parametric equation for a spiral. Now in terms of the components, we just add a z dot velocity, that's the z velocity, and a z double dot acceleration. Well, in this case, there's constant z velocity and no z acceleration. And then once again, we just do the derivatives to find, that's 0.03 by the way, theta dot, we have a non-constant here, depends on time, and we have a theta double dot term 0.06. So we substitute in here for velocity, we get 0.03 radially, we have a time-dependent angular velocity, because it's r times theta dot squared. This is a little bit messy. So that's r, that's theta dot squared. And then, of course, we have the 0.1 in the k direction, the third component of velocity. Okay, then for the acceleration, there's nothing. Then again, we've got this complicated expression, r times theta dot. And so that's the radial acceleration. Okay, so now in the angular direction, it's r. There's r. Theta double dot's non-zero here. It's 0.06. And we've got plus 2 times r dot times theta dot. So that has 2 angular terms then. 2 terms in the theta hat direction. And then there's nothing in the k direction.